Have you ever wondered if the universe might be computing you into existence right now? In laboratories around the world, quantum physicists are discovering something extraordinary. When particles behave differently, simply because we observe them, when reality seems to exist in multiple states until measured, when the fundamental building blocks of matter appear to follow rules remarkably similar to computer code, we begin to glimpse a possibility that would have sounded like science fiction just decades ago. The evidence is mounting that our reality might not be what we think it is. Welcome to another journey into the deepest mysteries of existence. I'm here to guide you through one of the most profound questions emerging from modern science. Tonight, we're exploring how quantum physics, the science of the very small, might be revealing that our entire universe operates more like a sophisticated simulation than the solid material reality we experience every day. Before we drift into these quantum depths together, take a moment to settle in wherever you are. Whether you're lying in bed watching the ceiling, curled up on a couch, or walking under the night sky, let yourself become comfortable with not knowing everything about the nature of reality. Sometimes, the most beautiful discoveries come when we allow ourselves to question what feels most certain. The story we're about to explore isn't just about particles and equations. It's about you, about consciousness itself, and about the possibility that the boundary between mind and matter might be far more fluid than we've ever imagined. This isn't a claim that's been proven beyond doubt. Rather, it's an invitation to consider evidence that's been quietly accumulating in physics laboratories for over a century. Evidence that suggests reality might be fundamentally different from our everyday experience. Let's begin with what might be the strangest experiment in the history of science. Picture a wall with two narrow slits cut into it. Behind the wall sits a screen that can detect where tiny particles land after passing through the slits. Now imagine firing electrons one at a time toward these slits. Common sense tells us each electron should go through one slit or the other, creating two bands of hits on the screen behind the wall. But that's not what happens. Instead, when no one is watching which slit each electron passes through, something remarkable occurs. The electrons create an interference pattern on the screen, with multiple bands of light and dark regions. This pattern can only form if each individual electron somehow goes through both slits simultaneously, interfering with itself like a wave rippling across water. Here's where it gets truly mysterious. The moment scientists place a detector to observe which slit each electron travels through, the interference pattern vanishes completely. The electrons suddenly behave like ordinary particles again, each going through only one slit and creating just two bands on the screen. The mere act of observation fundamentally changes what happens in the experiment. This isn't a malfunction of equipment or a subtle measurement error. This is the observer effect, and it's been confirmed in countless variations over nearly a century. Reality, at its most fundamental level, appears to behave differently when conscious observation is present versus when it's absent. As you contemplate this, notice how it challenges something we take for granted. We assume the world exists in definite states whether we're looking or not. Your coffee cup sits on the table with a specific temperature in a precise location, whether you're aware of it or not. But quantum mechanics suggests that at the deepest level, particles don't have definite properties until they're observed. They exist in what physicists call superposition, a state where all possible outcomes coexist simultaneously. Consider what this might mean. If the fundamental building blocks of everything, including your coffee cup and the table it sits on, only take on definite properties when observed, what does that tell us about the nature of reality itself? Some interpretations suggest this resembles how modern video games operate. A sophisticated game doesn't render every detail of its virtual world continuously. Instead, it uses computational shortcuts, only generating detailed graphics for areas currently being observed by the player. The rest remains in a simplified, probabilistic state until needed. This conserves processing power and makes complex virtual worlds possible. Could the universe operate according to similar principles? This remains unproven, but the parallel is striking. Just as a game engine only computes specific outcomes when a player observes a particular area, quantum systems seem to only resolve into definite states when conscious observation occurs. The implications ripple outward, like waves from a stone dropped in still water. If observation plays such a fundamental role in determining physical outcomes, what does this suggest about the relationship between consciousness and the material world? Are we passive observers of an independent reality, or are we somehow participating in its creation moment by moment? Every atom in your body contains a nucleus surrounded by electrons that don't orbit like tiny planets as we once imagined. Instead, these electrons exist in probability clouds, quantum superpositions of all possible locations and energies. Only when measured do they appear to occupy specific positions. This means that in a very real sense, you are made of quantum uncertainty held together by the strange rules of superposition and wave function collapse. But there's something even more intriguing happening in the quantum realm. Particles can become entangled, creating instantaneous correlations across vast distances that Einstein famously called spooky action at a distance. When two particles become entangled, measuring one immediately determines the state of the other, regardless of how far apart they are. This isn't information travelling between them faster than light. Rather, they appear to share a single quantum state that transcends ordinary notions of space and time. Think about what this means for a moment. If particles can maintain these instantaneous connections across the universe, it suggests that space and time, as we experience them, might be emergent properties rather than fundamental aspects of reality. They could be like the user interface of a computer program, a simplified way of presenting underlying information processing to conscious observers. This interpretation gained support from the mathematics of quantum mechanics itself. The equations that describe quantum systems are remarkably similar to information processing algorithms. When a quantum system evolves, it's performing calculations with probability amplitudes, manipulating information in ways that mirror how computer programs handle data. Quantum computers, which harness these effects for practical computation, demonstrate this connection explicitly. They use quantum bits or qubits that exist in superposition states, processing multiple possibilities simultaneously until measurement collapses them into definite outputs. In essence, quantum computers work by exploiting the same mysterious properties that govern all matter and energy in our universe. As you listen to this, take a breath and imagine what this could mean for you. Every thought you're having right now emerges from quantum processes in your brain. The neurons firing as you process these ideas rely on quantum mechanical effects in their molecular structures. If consciousness arises from quantum computation in biological systems, and if quantum mechanics reveals the computational nature of reality itself, then your awareness might be more deeply connected to the universe's information processing than we've ever realized. One of the most compelling pieces of evidence for a computational universe comes from the discovery that reality has a smallest possible scale. Just as a digital image is made of individual pixels that cannot be subdivided further, space and time appear to be quantized at the tiniest levels. This quantum graininess manifests through what physicists call Planck units. There's a minimum possible length, the Planck length, which is so small that 10 billion of them would fit across the width of a proton. Below this scale, the very concepts of distance and measurement lose meaning. Similarly, there's a minimum unit of time, the Planck time, representing the smallest possible duration in which any change can occur. This pixelation of reality extends beyond space and time to energy itself. Energy comes in discrete packets called quanta, which gave quantum mechanics its name. Just as a digital system processes information in bits that can only be 0 or 1, the universe appears to process physical changes in minimum increments that cannot be made smaller. The parallel to digital computation is striking. Any virtual reality system is fundamentally based on information processing, which means everything must ultimately be digitized into discrete units that cannot be subdivided further. The discovery that our universe operates according to similar discrete principles suggests that reality might indeed be computational at its foundation. But the pixelated nature of reality goes deeper than just minimum scales. The speed of light, one of the most fundamental constants in physics, might actually represent a processing speed limit rather than a property of space itself. Just as an overloaded computer processor slows down when handling too many calculations, Einstein's theory of general relativity shows that time itself slows down in regions of intense gravitational fields, where the curvature of space-time requires more complex calculations to maintain. Consider black holes, those mysterious objects where gravity becomes so intense that not even light can escape. Recent theoretical work suggests that black holes might function as cosmic information processors, encoding data on their surfaces in ways that mirror holographic storage systems. The information paradox surrounding black holes, which questions whether information can truly be destroyed, reads like a debate about data preservation in cosmic computing systems. As you contemplate these ideas, notice how they invite a shift in perspective. Instead of imagining yourself as a biological entity moving through empty space, you might consider the possibility that you are a pattern of information processing within a vast computational system. Your thoughts, your memories, your sense of continuity through time, all could be expressions of quantum information processing occurring at scales both incredibly tiny and unimaginably vast. This doesn't make your experience less real or meaningful. A character in a beautifully crafted story doesn't become less important because the story exists in language rather than stone. Similarly, if consciousness arises from information processing in a computational universe, your awareness, your relationships, your capacity for wonder and discovery remain as profound as ever. What we call the laws of physics might actually be something closer to the source code of reality. These mathematical relationships that govern everything from planetary orbits to atomic behavior display a precision and consistency that resembles well-designed software more than arbitrary natural phenomena. Consider the fine-tuning problem that has puzzled cosmologists for decades. The fundamental constants of nature, such as the strength of gravity, the electromagnetic force, and the expansion rate of the universe, appear to be calibrated with extraordinary precision to allow for the existence of stars, planets, and ultimately life itself. If any of these values were even slightly different, the universe would be either too chaotic for stable structures to form, or too static for complexity to emerge. In traditional physics, this fine-tuning is often explained through the multiverse hypothesis, suggesting that we exist in one of countless universes, and naturally find ourselves in one where the constants allow for our existence. But there's another possibility that quantum physics makes increasingly plausible. These constants might be intentionally set parameters in a cosmic simulation, carefully chosen to create a universe capable of supporting conscious observers. The mathematical elegance of physical laws supports this interpretation. Equations like Einstein's E equals mc squared or Schrödinger's wave equation possess a beauty and simplicity that programmers recognize in well-written code. They're compact, powerful, and govern complex behaviors through relatively simple rules. This resembles how sophisticated computer programs can generate vast virtual worlds through underlying algorithms that are mathematically elegant yet computationally efficient. Cellular automata research provides concrete examples of how simple rules can generate complex realities. A cellular automaton is a grid of cells that change states based on the states of their neighbours according to fixed rules. Despite their simplicity, these systems can produce patterns of stunning complexity, including structures that appear to move, reproduce, and interact in ways that mirror biological or physical processes. Some physicists propose that our universe might operate as a vast cellular automaton, with space itself forming a computational grid where each point processes information according to quantum mechanical rules. Changes propagate through this grid at the speed of light, which would represent the maximum processing speed of the underlying system. Take a moment to let this possibility settle in your awareness. If physical laws are computational rules running on a cosmic information processing system, then every natural phenomenon you've ever witnessed, from the way light reflects off water to the spiral structure of galaxies, represents the execution of elegant algorithms designed to create a coherent, navigable reality for conscious beings like yourself. This perspective doesn't diminish the wonder of natural beauty. A sunset remains breathtaking whether it emerges from the scattering of photons through atmospheric particles or from the execution of light-rendering algorithms in a cosmic simulation. The experience of beauty, the sense of connection with something larger than yourself, the capacity for awe and wonder, these qualities of consciousness remain profound regardless of the underlying computational substrate that makes them possible. Perhaps the most profound implication of quantum physics isn't what it reveals about particles or waves, but what it suggests about the nature of consciousness itself. When we observe that reality seems to shift based on conscious observation, we're confronted with a possibility that challenges our most basic assumptions about the relationship between mind and matter. In the traditional view of science, consciousness is something that emerges from complex arrangements of matter. Neurons fire, chemicals flow, and somehow the subjective experience of being you arises from these physical processes. But quantum mechanics hints at something more mysterious. What if consciousness isn't just a product of physical processes, but is somehow fundamental to the way reality operates? The delayed choice quantum eraser experiment pushes this mystery even further. In this variation of the double slit experiment, scientists can choose whether to observe which path a particle took even after the particle has already been detected. Remarkably, the decision about whether to make this observation affects the pattern that appears on the detector screen, as if the present choice somehow influences what happened in the past. This suggests that the role of observation in quantum mechanics isn't just about the moment of measurement. It's about the entire context of conscious intention and choice. Some interpretations propose that consciousness doesn't just reveal pre-existing reality, but participates in determining which version of reality becomes actualized from the quantum field of possibilities. Take a quiet moment to consider what this might mean for your experience right now. As you process these ideas, as your awareness moves from thought to thought, you might be participating in a fundamental process that shapes reality at the quantum level. This isn't to suggest that your thoughts directly control external events, but rather that consciousness and physical reality might be more intimately connected than we've ever imagined. The Copenhagen interpretation of quantum mechanics, developed by Niels Bohr and Werner Heisenberg, essentially states that quantum systems don't have definite properties until measured. This interpretation has guided physics for nearly a century, despite its strange implications. If we take it seriously, it suggests that reality exists in a state of potential until consciousness interacts with it. Some researchers, like former NASA physicist Thomas Campbell, have proposed that this observer effect indicates we live in what he calls a virtual reality that's computed for consciousness on demand. In this view, reality operates like a sophisticated simulation that only renders specific outcomes when conscious beings observe them. The universe conserves computational resources by maintaining quantum possibilities in superposition until observation requires a definite result. This interpretation remains highly speculative and lacks scientific consensus. However, it offers a framework for understanding why quantum mechanics behave so strangely from our classical perspective. If consciousness and computation are fundamental aspects of reality rather than emergent properties, then the observer effect becomes less mysterious and more like a natural feature of how information processing systems operate. As you contemplate this possibility, notice how it might shift your sense of agency in the world. If consciousness plays a fundamental role in determining which quantum possibilities become actualized, then your awareness isn't just passively observing reality, but actively participating in its unfolding. This doesn't mean you can wish material changes into existence, but it suggests that the boundary between observer and observed might be more fluid than classical physics assumed. The emergence of digital physics as a scientific framework represents one of the most radical shifts in how we understand reality since the dawn of modern science. This field proposes that information, not matter or energy, forms the fundamental substrate from which everything else emerges. It's a perspective that transforms particles and forces into patterns of information processing and space-time itself into a computational medium. Physicist John Wheeler captured this revolutionary idea in his famous phrase, "it from bit," suggesting that all physical phenomena arise from binary information processing at the most fundamental level. In this view, what we experience as solid matter is actually the result of information patterns being processed according to the rules we call physical laws. The mathematical structure of quantum mechanics supports this information theoretic interpretation. Quantum states can be described as information patterns, quantum operations as information processing, and quantum measurements as information extraction. When a quantum system evolves according to Schrödinger's equation, it's essentially performing calculations with probability amplitudes, manipulating information in ways that closely parallel how computer algorithms process data. Consider the holographic principle, one of the most startling discoveries in modern theoretical physics. This principle suggests that all the information contained in a volume of space can be encoded on its boundary. Much like a hologram stores three-dimensional information on a two-dimensional surface. If this principle applies to our universe, it implies that the three-dimensional reality we experience might be a projection of information processing occurring on a lower dimensional substrate. Black hole physics provides compelling evidence for the holographic principle. Stephen Hawking's work on black hole thermodynamics revealed that these objects have temperatures and entropies that depend on their surface areas rather than their volumes. This suggests that black holes store information on their surfaces, processing and encoding data in ways that mirror holographic storage systems. Some physicists propose that black holes might function as cosmic information processors, with their event horizons serving as computational interfaces between different regions of space-time. The concept of quantum error correction, developed for quantum computing, offers another window into the computational nature of reality. Quantum computers are incredibly fragile because quantum states are easily disturbed by environmental interference. To maintain coherent quantum computation, these systems require sophisticated error correction protocols that constantly monitor and adjust quantum information to prevent corruption. Remarkably, similar error correction mechanisms appear to operate in fundamental physics. The laws of nature display a remarkable stability and consistency that resembles well-designed error correction systems. Physical constants remain constant. Conservation laws hold across vast scales of time and space, and the mathematical relationships governing natural phenomena maintain their precision despite the chaotic complexity of real-world systems. Some researchers suggest that apparent anomalies in physics might represent error correction processes in an underlying computational system. When experimental results suddenly change or physical constants appear to shift slightly, these could be instances of cosmic debugging, where the underlying information processing system corrects accumulated computational errors to maintain consistency. As you absorb these ideas, take a moment to appreciate how they reframe your place in the cosmos. If reality is fundamentally informational, then your consciousness might represent a unique form of information processing within the universal computation. Your thoughts, memories, and experiences would be patterns of information that arise from and contribute to the ongoing cosmic calculation that generates the appearance of physical reality. This perspective doesn't diminish the importance of your experience or the reality of your relationships and emotions. Information patterns can be just as meaningful and beautiful as material structures. A symphony exists as information patterns in sound waves and neural responses, but its beauty and emotional impact are no less real for being informational rather than material. The possibility that our reality might be a simulation received rigorous philosophical treatment from Oxford philosopher Nick Bostrom in his groundbreaking 2003 paper. Bostrom's simulation argument doesn't claim that we definitely live in a simulation, but rather demonstrates that at least one of three propositions must be true, and each possibility has profound implications for how we understand our existence. The first proposition suggests that civilizations typically go extinct before developing the computational power needed to run detailed simulations of their ancestors. If this is true, it would explain why we don't observe advanced civilizations running such simulations. But it also implies a rather pessimistic future for technological species like ourselves. The second proposition proposes that Even if civilizations survive to develop such capabilities, they choose not to run ancestor simulations. Perhaps ethical considerations, resource limitations, or simple lack of interest prevents advanced civilizations from creating detailed simulations of their evolutionary history. This possibility suggests that technological advancement might be accompanied by a shift in values that makes simulation projects less appealing. The third proposition, and the most startling, is that most observers could be simulated. If advanced civilizations do run ancestor simulations, and if they run many of them, then the total number of simulated beings would vastly outnumber biological beings. By simple probability, any randomly selected conscious being would be more likely to be simulated rather than biological. Bostrom's argument relies on a type of reasoning called anthropic probability, which considers the likelihood of finding yourself in different types of possible worlds. If simulated worlds greatly outnumber base reality worlds, and if simulated consciousness is indistinguishable from biological consciousness, then most conscious observers would find themselves in simulations rather than base reality. The implications of each possibility stretch far beyond philosophy into questions of ethics, meaning, and purpose. If we live in base reality, we bear the responsibility of potentially creating simulated beings in the future, raising profound questions about our obligations to artificial consciousness. If we live in a simulation, it challenges traditional notions of authenticity and raises questions about the nature of moral responsibility within simulated environments. Some interpretations suggest that the simulation hypothesis, rather than diminishing the meaning of existence, might actually enhance it. A simulated world created by advanced beings might be designed with intentional purposes, carefully crafted to provide meaningful experiences and opportunities for growth and discovery. The fine-tuning of physical constants that allows for complexity in life might reflect intentional design rather than cosmic coincidence. Recent advances in artificial intelligence and virtual reality make the simulation hypothesis increasingly plausible from a technological standpoint. As we develop more sophisticated simulations ourselves, we gain insight into how advanced civilizations might approach the challenge of creating convincing, simulated realities. Each improvement in our computational capabilities makes it easier to imagine how a sufficiently advanced civilization could create simulations indistinguishable from base reality. Take a breath and allow yourself to sit with the uncertainty these ideas generate. Whether you exist in base reality or within a simulation, your experience of consciousness, your capacity for wonder and discovery, your relationships and emotions remain equally real and meaningful. The search for truth, the appreciation of beauty, the cultivation of wisdom and compassion, these pursuits retain their value regardless of the computational substrate that might underlie them. If you find yourself drawn to these explorations of consciousness and reality, members of our community receive each episode 48 hours early, completely ad-free, allowing for deeper immersion in these contemplative journeys. You can join them whenever you feel ready, but there's no pressure to decide right now. The simulation argument ultimately invites us to hold our assumptions about reality more lightly, while taking our experiences and choices more seriously. If we can't definitively determine whether we live in base reality or a simulation, perhaps the most meaningful response is to live with curiosity, compassion, and wonder, appreciating the mystery while engaging fully with whatever reality we find ourselves inhabiting. If quantum physics suggests that reality operates according to computational principles, what does this mean for consciousness itself? The hard problem of consciousness, how subjective experience arises from objective processes, takes on new dimensions when viewed through the lens of quantum computation and information processing. Traditional neuroscience approaches consciousness as an emergent property of complex neural networks. Billions of neurons communicate through electrochemical signals, and somehow this biological computation gives rise to the unified experience of being aware. But quantum physics suggests that consciousness might be more fundamental than this picture implies. Quantum effects occur throughout biological systems, including the brain. Microtubules within neurons, the protein structures that give cells their shape and organization, appear to maintain quantum coherence even in the warm, noisy environment of living tissue. Some researchers propose that these quantum processes in microtubules might be essential for consciousness, allowing the brain to perform quantum computations that classical neural networks couldn't achieve. The physicist and mathematician Roger Penrose, working with anesthesiologist Stuart Hameroff, developed a theory called orchestrated objective reduction, which proposes that consciousness arises from quantum computations in microtubules. In their model, consciousness emerges when quantum superpositions in these cellular structures collapse in coordinated ways across the brain, creating unified moments of aware experience. This theory remains highly controversial within neuroscience, as most researchers believe quantum effects would be too fragile to persist in biological systems. However, recent discoveries of quantum coherence in photosynthesis and possibly in avian navigation suggest that life has evolved ways to harness quantum effects for biological functions. Perhaps consciousness represents the most sophisticated application of quantum biology, using quantum computation to generate the unified field of awareness that characterizes conscious experience. If consciousness does involve quantum computation, it suggests a deep connection between mind and the fundamental information processing that appears to underlie physical reality. Your thoughts wouldn't just be patterns of neural activity, but quantum information processing events that participated in the same computational substrate that generates physical phenomena. Consider what happens when you form a memory or make a decision. In the quantum computational view, these mental processes involve the manipulation of quantum information states within biological systems. The creation of a memory might involve encoding information into quantum states that can be maintained through biological quantum error correction mechanisms. Decision-making might involve quantum superpositions of possible choices that collapse into definite outcomes through processes similar to quantum measurements. The binding problem in neuroscience asks how the brain integrates information from different sensory modalities and neural regions into unified conscious experiences. Classical neural networks struggle to explain how distributed information processing creates the seamless unity of consciousness. Quantum entanglement offers a potential solution, suggesting that different parts of the brain might become quantum mechanically correlated, creating instantaneous connections that could unify distributed information processing into coherent conscious states. This quantum approach to consciousness also addresses the question of how conscious observation might influence quantum systems. If consciousness involves quantum information processing, then conscious observation of quantum systems might represent the interaction between different levels of quantum computation. The observer effect wouldn't be mysterious interference by consciousness into physical systems, but rather the natural result of quantum computational systems interacting with each other. As you reflect on these possibilities, notice the quality of your own awareness right now, the unity of your conscious experience, the way different thoughts and sensations flow together into a coherent stream of awareness might represent quantum computational processes that connect your individual consciousness to the broader information processing network that generates physical reality. This perspective suggests that meditation and contemplative practices might involve learning to consciously participate in quantum information processing. When you observe your thoughts without attachment, when you cultivate states of open awareness, you might be learning to navigate quantum computational states more skillfully, developing greater sensitivity to the information processing that underlies both consciousness and physical reality. The implications extend to questions of free will and agency. If consciousness involves quantum computation, then your choices might emerge from quantum superpositions of possibilities that collapse into definite decisions through processes that involve both deterministic computation and genuine quantum randomness. This could provide a middle path between complete determinism and arbitrary randomness, suggesting that conscious choice involves creative participation in quantum information processing. These ideas remain speculative, representing interpretations of quantum mechanics rather than established scientific facts. However, they offer a framework for understanding consciousness that honors both the scientific insights of quantum physics and the irreducible reality of subjective experience. Whether or not consciousness literally involves quantum computation, the parallels between quantum information processing and the characteristics of conscious experience suggest deep connections between mind and the fundamental nature of reality. In the depths of Einstein's equations lies a curious constant that might be more than just a property of space and time. The speed of light, that universal limit of 299,792,458 meters per second, has puzzled physicists not just for what it represents, but for why such a limit should exist at all. In a truly infinite, continuous reality, why would there be a maximum speed for information transfer? The answer might lie in recognizing this speed limit as something remarkably familiar to anyone who has watched a computer struggle with too many tasks. When a processor becomes overloaded, the system slows down, operations take longer, and eventually the entire system may freeze. What if the speed of light represents not a fundamental property of space, but rather the processing speed limit of the computational substrate underlying reality? This interpretation gained support from one of the strangest predictions of relativity theory. As objects approach the speed of light, time itself begins to slow down relative to stationary observers. At extreme speeds, time dilation becomes so pronounced that a journey lasting years for an outside observer might feel like minutes to the traveller. This resembles nothing so much as a computer system running out of processing power, where operations that should happen quickly begin to lag as the system reaches its computational limits. Consider the environment around a black hole, where gravity becomes so intense that space-time curves dramatically. Here, time dilation reaches extreme proportions, with time flowing much more slowly near the event horizon than in regions of weaker gravitational fields. If we interpret gravitational fields as regions where space-time requires more intensive computation to maintain its structure, then time dilation becomes a natural consequence of computational load balancing in a cosmic information processing system. The mathematics of general relativity describe how mass and energy curve space-time, creating the phenomena we experience as gravity. But these same equations can be interpreted as describing how information density affects the computational requirements for maintaining local spacetime geometry. Massive objects like stars and planets represent regions of high information density that require more processing power to simulate accurately, naturally leading to the time dilation effects we observe. Take a moment to imagine what this means for your experience of time right now. The steady passage of seconds, the rhythm of your breathing, the flow of thoughts through your awareness. All of these temporal experiences might reflect the steady processing rate of cosmic computation occurring at scales both infinitely small and unimaginably vast. You exist within time not as a passive observer, but as a pattern of information processing, participating in the universal computation that generates the experience of temporal flow. This computational interpretation of relativity also addresses one of the most perplexing aspects of physics, the relationship between quantum mechanics and gravity. Quantum field theory works beautifully at small scales, while general relativity accurately describes large-scale gravitational phenomena. But attempts to unify these theories into a quantum theory of gravity have faced enormous challenges, leading some physicists to wonder if they're approaching the problem from the wrong direction. If both quantum mechanics and relativity emerge from underlying information processing, their apparent incompatibility might reflect different computational regimes, rather than fundamentally different physics. Quantum effects might represent the discrete, probabilistic nature of computation at the smallest scales, while relativistic effects might emerge from resource management in large-scale information processing. The search for quantum gravity becomes a quest to understand how computational processes scale from quantum information processing to classical space-time simulation. The cosmic microwave background radiation, that faint glow left over from the early universe, provides another window into the computational nature of reality. This radiation fills all of space with a remarkable uniformity, showing only tiny variations that later grew into galaxies and larger structures. The statistical properties of these fluctuations match exactly what would be expected from quantum information processing during the universe's earliest moments. Some interpretations suggest that the cosmic microwave background represents a kind of initialization pattern, the quantum computational state from which the universe's current complexity evolved. Like the random seed values that initialize a sophisticated computer simulation, these primordial fluctuations might encode the initial conditions from which all subsequent cosmic evolution emerged through natural information processing algorithms. Deep within the quantum realm exists a phenomenon so strange that it seems to violate our most basic assumptions about the nature of barriers and boundaries. Quantum tunneling allows particles to pass through obstacles that should be completely impenetrable according to classical physics. An electron encountering an energy barrier it lacks sufficient energy to overcome doesn't simply bounce back. Instead, there's a probability it will appear on the other side, as if it had walked through a solid wall. This isn't a rare or exotic effect confined to laboratory experiments. Quantum tunneling is essential for the nuclear fusion that powers the Sun. The protons in stellar cores don't actually have enough energy to overcome their mutual electrical repulsion through classical means. Yet fusion occurs because quantum tunneling allows these particles to bypass the energy barriers that would otherwise keep them apart. Every ray of sunlight that has ever warmed your face exists because of quantum tunneling in the solar core. The tunneling effect reveals something profound about the nature of barriers in quantum mechanics. What appears solid and impenetrable at our scale becomes probabilistic and permeable at the quantum level. The wave function describing a particle doesn't simply stop at a barrier. Instead, it extends beyond the obstacle, creating a non-zero probability for the particle to manifest on the other side. This behavior mirrors how sophisticated simulations handle boundary conditions and collision detection. In many virtual environments, objects don't have perfectly solid boundaries, but rather probability fields that determine interaction outcomes. A character in a game might occasionally pass through walls due to computational approximations or deliberate design choices that prioritize smooth gameplay over perfect boundary enforcement. Some interpretations suggest that quantum tunneling might represent computational shortcuts in the universe's information processing. Rather than calculating the exact classical trajectory that would be required for a particle to go around or over an obstacle, the system allows for probabilistic boundary crossing that achieves similar outcomes with less computational overhead. This would be similar to how computer graphics use approximations and shortcuts to create convincing visual effects without perfectly simulating every physical detail. The scanning tunneling microscope demonstrates how quantum tunneling can be harnessed for practical applications. This instrument uses the tunneling effect to map surfaces at the atomic level, allowing scientists to literally see individual atoms. The microscope works by bringing a sharp probe very close to a surface, close enough that electrons can tunnel between the probe and the sample. The tunneling current varies with the distance and local properties of the surface, creating detailed maps of atomic scale structures. As you contemplate these ideas, notice how quantum tunneling challenges our intuitive understanding of boundaries and limitations. In your daily life, walls are solid, containers have impermeable boundaries, and obstacles require energy to overcome. Yet at the quantum level that underlies all material reality, these absolute boundaries dissolve into probabilities and possibilities. This dissolution of absolute boundaries might extend to other aspects of reality that we typically think of as fixed and definite. The boundaries between self and environment, between past and future, between possible and actual, might be more fluid at fundamental levels than our classical experience suggests. Quantum mechanics reveals a universe where the rigid categories of everyday experience give way to subtle interconnections and probabilistic relationships. Radioactive decay provides another example of quantum tunneling with profound implications for our understanding of time and causation. The alpha particles trapped within atomic nuclei don't have enough energy to escape, according to classical physics, yet they tunnel out at statistically predictable rates. We can calculate the half-life of radioactive elements with remarkable precision, knowing that exactly half the atoms in a sample will decay over a specific time period, but we cannot predict which individual atoms will decay or when. This combination of statistical predictability and individual indeterminacy reflects a fundamental characteristic of quantum systems. The universe appears to operate according to probabilistic laws that generate reliable statistical outcomes from inherently unpredictable individual events. This resembles how computer simulations use random number generators to create unpredictable individual outcomes that nevertheless follow statistical distributions over large samples. The implications of quantum tunneling extend beyond physics into questions about the nature of possibility itself. If particles can tunnel through barriers that should be impenetrable, what does this suggest about other apparently impossible transitions? While we cannot directly apply quantum tunneling to macroscopic objects or life situations, the underlying principle that absolute barriers might be more permeable than they appear offers a different way of thinking about obstacles and limitations. One of the most startling discoveries in modern theoretical physics suggests that our three-dimensional reality might be a projection from information encoded on a distant two-dimensional surface. The holographic principle, emerging from black hole physics and string theory research, proposes that all the information contained within a volume of space can be encoded on its boundary. Much like a hologram stores three-dimensional images on flat surfaces. This principle emerged from attempts to understand black hole thermodynamics. Stephen Hawking's work revealed that black holes have temperatures and entropies that depend on their surface areas rather than their volumes. This suggested that black holes store information on their event horizons, the two-dimensional boundaries that separate their interiors from the external universe. If black holes encode volumetric information on their surfaces, perhaps this principle applies more generally to all of space-time. The implications stretch far beyond black hole physics. If the holographic principle applies to our observable universe, then everything you experience, every star, planet, and particle, might be a three-dimensional projection of information processing occurring on a distant cosmic boundary. Your sense of depth, your feeling of moving through three-dimensional space, your perception of objects having internal volume and structure, all might emerge from computations performed on a two-dimensional substrate. This doesn't make your experience less real, but it fundamentally reframes what reality means. A holographic image appears three-dimensional and contains all the information of the original three-dimensional scene, even though it's encoded on a flat surface. Similarly, a holographically projected reality would contain all the information and experiential richness of three-dimensional existence, while being fundamentally two-dimensional in its information encoding. The holographic principle offers elegant solutions to several puzzles in physics. The information paradox that arises when matter falls into black holes asks whether information can be truly destroyed when it crosses the event horizon. If information is encoded on the black hole's surface rather than lost in its interior, then the paradox dissolves. Information is never destroyed, only encoded in different forms on the boundary. Recent research in quantum gravity suggests that space-time itself might emerge from entanglement relationships between information on holographic boundaries. In this view, the three-dimensional space you inhabit doesn't exist independently, but emerges from correlations in quantum information processing occurring on distant surfaces. Distance, volume, and dimensionality become emergent properties rather than fundamental aspects of reality. Take a breath and consider what this might mean for your sense of location and embodiment right now. The feeling of being here in this specific place, surrounded by three-dimensional space, might reflect information processing patterns that create the experience of locality and embodiment without requiring that you literally occupy a three-dimensional volume. Your consciousness might be more like a pattern of activity in a holographic encoding than a thing located at a specific point in space. The holographic principle also connects to information theory in profound ways. The maximum amount of information that can be encoded in any region of space appears to be proportional to the area of its boundary rather than its volume. This suggests that information, not space itself, provides the fundamental limitation on reality structure. The universe might be more like a vast information processing system that creates the experience of three-dimensional space rather than a three-dimensional container filled with information. Computer graphics provides helpful analogies for understanding holographic reality. Modern video games create convincing three-dimensional environments that exist only as mathematical descriptions processed by graphics hardware. Players experience rich, detailed worlds with depth, texture, and spatial relationships, but these worlds exist as information patterns rather than physical volumes. The holographic principle suggests that physical reality might operate according to similar principles, with three-dimensional experience emerging from information processing rather than from literal three-dimensional existence. String theory, one of the leading candidates for a unified theory of quantum gravity, heavily relies on holographic principles. In string theory, the fundamental constituents of reality are one-dimensional strings vibrating in higher dimensional spaces. The holographic principle suggests that all the physics occurring in these higher dimensional spaces can be equivalently described by information processing on their lower dimensional boundaries. This creates a remarkable possibility that our four-dimensional space-time, with its three dimensions of space and one of time, might be holographically equivalent to information processing occurring in fewer dimensions. The rich complexity of physical reality, with all its particles, forces, and structures, might emerge from simpler computational processes occurring on cosmic boundaries we cannot directly observe. As you absorb these ideas, notice how they invite a shift in your relationship with physical space. Rather than imagining yourself as a solid object moving through empty space, you might consider the possibility that both you and the space you seem to inhabit emerge from information processing patterns that create the experience of three-dimensional embodied existence. This holographic perspective doesn't diminish the reality of your experience or the importance of your relationships and activities. A character in a beautifully rendered three-dimensional game world has genuine experiences within that world, forms meaningful relationships with other characters, and can accomplish significant goals within the game's narrative structure. The holographic nature of the world's encoding doesn't make these experiences less valuable or meaningful. At the heart of quantum mechanics lies perhaps its most perplexing puzzle, the measurement problem. This challenge goes beyond technical details to touch fundamental questions about the role of consciousness in physical reality. When quantum systems exist in superposition, maintaining multiple potential states simultaneously, what causes them to collapse into definite outcomes? And why does this collapse seem to occur precisely when conscious observation takes place? The traditional Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, sidesteps this question by asserting that quantum systems simply don't have definite properties until measured. This interpretation has guided physics for nearly a century, despite its counterintuitive implications. It suggests that reality exists in a state of potential until consciousness interacts with it, transforming possibilities into actualities through the act of observation. Some physicists, uncomfortable with consciousness playing such a central role in physical processes, have proposed alternative interpretations. The many worlds interpretation suggests that all quantum possibilities actually occur, with reality branching into parallel universes for each outcome. In this view, consciousness doesn't collapse wave functions, but rather selects which branch of the multiverse we experience. The spontaneous collapse theories propose that wave functions collapse randomly according to objective physical processes without requiring conscious observers. Yet none of these alternatives fully resolves the deep mystery of why quantum systems behave so differently when observed versus unobserved. The delayed choice quantum eraser experiment pushes this mystery even further, demonstrating that the decision to observe can apparently influence outcomes retroactively. Scientists can choose whether to measure which path a particle took even after the particle has already been detected, and this future choice affects the pattern that appears in the detection results. These experiments suggest that the relationship between consciousness and quantum mechanics might be more fundamental than mere measurement disturbance. Some interpretations propose that consciousness doesn't just reveal pre-existing reality, but participates in determining which version of reality becomes actualized from the quantum field of possibilities. This remains a highly speculative idea without scientific consensus, but it opens profound questions about the nature of conscious observation and its role in physical processes. Consider what happens in your own experience of observation right now. When you direct your attention to the sensations in your hands, to sounds in your environment, or to thoughts arising in your mind, you're engaging in the same fundamental process that plays such a mysterious role in quantum mechanics. The act of conscious observation, whether directed toward quantum systems or everyday experiences, involves the transformation of potential awareness into definite conscious content. Some researchers have proposed that consciousness itself might operate according to quantum mechanical principles. If awareness involves quantum information processing in biological systems, then conscious observation of quantum systems might represent the interaction between different levels of quantum computation. The observer effect wouldn't be mysterious interference by consciousness into physical systems, but rather the natural result of quantum computational systems interacting with each other. This quantum approach to consciousness addresses several puzzles in neuroscience and philosophy of mind. The binding problem asks how the brain integrates information from different sensory modalities and neural regions into unified conscious experiences. Classical neural networks struggle to explain how distributed information processing creates the seamless unity of consciousness. Quantum entanglement offers a potential solution, suggesting that different parts of the brain might become quantum mechanically correlated, creating instantaneous connections that could unify distributed information processing into coherent conscious states. The hard problem of consciousness, how subjective experience arises from objective processes, takes on new dimensions when viewed through quantum information theory. If consciousness involves quantum computation, then subjective experience might represent the internal perspective of quantum information processing systems. What we call qualia, the subjective qualities of conscious experience, might be the intrinsic characteristics of quantum computational processes viewed from within rather than from external observation. As you reflect on these possibilities, take a moment to appreciate the mystery of your own awareness. The fact that you can observe your thoughts, notice your emotions, and direct your attention represents one of the most remarkable phenomena in the known universe. Whether or not consciousness literally involves quantum computation, the parallels between quantum information processing and the characteristics of conscious experience suggest deep connections between mind and the fundamental nature of reality. The implications extend to questions of free will and agency. If consciousness involves quantum computation, then your choices might emerge from quantum superpositions of possibilities that collapse into definite decisions through processes that involve both deterministic computation and genuine quantum indeterminacy. This could provide a middle path between complete determinism and arbitrary randomness, suggesting that conscious choice involves creative participation in quantum information processing rather than being either fully determined or completely random. These ideas remain speculative, representing interpretations of quantum mechanics rather than established scientific facts. However, they offer a framework for understanding consciousness that honors both the scientific insights of quantum physics and the irreducible reality of subjective experience. Whether or not consciousness literally involves quantum computation, the measurement problem in quantum mechanics points toward deep mysteries about the relationship between mind and matter that continue to challenge our understanding of reality itself. Time, perhaps more than any other aspect of reality, challenges our understanding when viewed through the lens of quantum physics and information theory. Our everyday experience suggests that time flows uniformly from past to future, with causes preceding effects in a clear linear sequence. Yet quantum mechanics reveals temporal relationships that are far stranger and more fluid than this classical picture suggests. The delayed choice quantum eraser experiment demonstrates that quantum systems can exhibit what appears to be retroactive influence, where decisions made in the present seem to affect outcomes that occurred in the past. This doesn't violate causality in the sense of sending information backward in time, but it suggests that the temporal relationships in quantum systems are more subtle and interconnected than our linear intuitions assume. If reality operates according to computational principles, then these strange temporal effects might reflect how information processing systems handle time and causation. In computer simulations, the appearance of linear time often emerges from computational processes that don't themselves unfold in linear sequence. A program might calculate the entire trajectory of a particle before rendering its motion frame by frame, or it might use predictive algorithms that incorporate future states to determine present behaviors. The block universe interpretation of relativity theory suggests that all moments of time exist simultaneously, like frames in a film reel. Past, present, and future are equally real, with the passage of time being more like the movement of consciousness through a static four-dimensional structure. This interpretation aligns naturally with computational views of reality, where the entire temporal evolution of a system might be calculated as a complete information structure, rather than unfolding moment by moment. Consider what this might mean for your experience of memory and anticipation. The memories that seem to connect you to your past and the expectations that orient you toward the future might not represent connections to temporally distant events, but rather access to different parts of a comprehensive information structure that contains your entire temporal existence. Your sense of being located at a particular moment in time might be analogous to a character in a story being aware of the current chapter while the entire narrative exists as a complete structure. Quantum entanglement adds another layer to these temporal mysteries. When particles become entangled, they maintain instantaneous correlations regardless of spatial separation, suggesting that space doesn't fundamentally limit quantum relationships. Some interpretations propose that entanglement might extend across time as well as space, creating correlations between quantum states at different temporal locations. This temporal entanglement could provide a mechanism for the apparently retroactive effects observed in delayed choice experiments. If quantum states at different times can become entangled, then measurements performed at later times might influence the properties of earlier states through these temporal quantum correlations. The apparent flow of influence backward in time might actually reflect a temporal relationships that transcend our linear conception of temporal causation. The computational universe hypothesis offers a framework for understanding these temporal anomalies. In information processing systems, causation often differs from temporal sequence. A program might use future states to calculate present outputs, or it might maintain global constraints that ensure consistency across all temporal locations simultaneously. The apparent paradoxes of quantum temporal effects might reflect similar computational processes operating at the level of fundamental physics. Take a moment to reflect on your own experience of temporal flow right now. The sense of duration as you listen to these words, the feeling that thoughts arise and pass away in sequence, the impression that you're moving from past moments toward future ones, all might reflect computational processes that create the experience of temporal passage rather than literal movement through time. This computational perspective on time also addresses questions about free will and determinism. If the future already exists in some sense, as suggested by the block universe interpretation, does this mean that all events are predetermined? The computational view suggests a more nuanced possibility. Even if all temporal states exist simultaneously in the complete information structure of reality, conscious choice might involve participating in the computational processes that determine which version of that structure becomes actualized. Your decisions might not change a predetermined future, but rather participate in determining which of many possible complete temporal structures corresponds to the reality you experience. Free will becomes not the ability to change the future, but the capacity to participate consciously in the computational processes that generate the entire temporal structure of existence. The arrow of time, the apparent directionality that distinguishes past from future, presents another puzzle that computational interpretations might help resolve. In fundamental physics, most equations work equally well in both temporal directions, yet we experience a clear distinction between past and future. This asymmetry might reflect computational processes that have inherent directionality, such as information processing systems that compute future states from present conditions while maintaining records of past states. Entropy, the tendency of systems to become more disordered over time, provides one explanation for time's arrow. But if reality is computational, entropy might reflect the natural tendency of information processing systems to explore increasingly complex computational states. The arrow of time might point in the direction of increasing computational complexity rather than simply increasing disorder. The observer effect in quantum mechanics reveals something profound about the relationship between consciousness and physical reality. When particles behave as waves until observed, then suddenly collapse into definite particle-like states upon measurement, we encounter a phenomenon that challenges the fundamental assumption that reality exists independently of conscious observation. This isn't simply about measurement apparatus disturbing delicate systems, but about the apparent role of observation itself in determining physical outcomes. Double-slit experiments have been performed with individual photons, electrons, and even large molecules, consistently demonstrating that the presence or absence of observation fundamentally alters the nature of the phenomena being studied. When no measurement is made to determine which path a particle takes, it exhibits wave-like interference patterns that can only result from passing through both slits simultaneously. The moment observation occurs, this wave-like behavior vanishes, and the particle behaves classically, going through one slit or the other. This transformation doesn't depend on the physical impact of measurement devices. Experiments have been designed where the potential for observation exists without actual measurement taking place, and even this potential seems to influence outcomes. The quantum system appears to know whether information about its state could, in principle, be obtained by a conscious observer, suggesting that the relationship between consciousness and quantum mechanics goes deeper than simple measurement disturbance. Some interpretations propose that consciousness plays an active role in collapsing quantum wave functions, transforming potential realities into definite outcomes through the act of conscious observation. This remains a highly speculative idea without scientific consensus, but it points toward fundamental questions about the nature of conscious awareness and its relationship to physical processes. If consciousness does participate in quantum state collapse, then awareness isn't simply a passive mirror reflecting pre-existing reality, but an active participant in determining which version of reality becomes manifest. Consider what this might mean for your experience right now. As you direct your attention to different aspects of your environment, to sensations in your body, or to thoughts arising in your mind, you might be participating in processes that share fundamental similarities with quantum measurement. The act of conscious observation, whether applied to quantum systems or everyday experience, involves the transformation of potential awareness into definite conscious content. The delayed choice quantum eraser experiment pushes these implications even further. In this sophisticated variation of the double slit experiment, researchers can choose whether to obtain which path information about a particle even after it has already been detected. Remarkably, this retroactive choice seems to influence the interference pattern that appears in the detection results, as if the present decision about observation affects what happened in the past. This doesn't violate causality in the sense of sending information backward through time, but it suggests that quantum systems exist in states of potential until the complete observational context is established. The particle doesn't decide how to behave until the entire measurement situation, including future choices about observation, is determined. This implies that quantum systems might exist in extended temporal relationships that transcend our ordinary understanding of sequential time. The role of information in quantum mechanics provides another perspective on the observer effect. Quantum systems seem to behave differently depending on whether information about their states is available to conscious observers, regardless of how that information might be obtained. This suggests that information accessibility, rather than physical measurement disturbance, might be the key factor in quantum state collapse. If reality is fundamentally informational, as suggested by digital physics interpretations, then consciousness might represent a unique form of information processing that has special relationships with other information processing systems in nature. Conscious observation might involve the integration of quantum information into the particular type of information processing that generates conscious experience, causing quantum systems to transition from superposition states to definite outcomes. Take a breath and notice the quality of your awareness as you absorb these ideas. The capacity to observe, to be consciously present with experience as it unfolds, might represent something more profound than passive reception of sensory information. If consciousness participates in fundamental physical processes through observation, then awareness becomes a creative force in the ongoing generation of experienced reality. This perspective doesn't suggest that you can control quantum outcomes through wishful thinking or that consciousness directly manipulates physical events according to personal desires. Rather, it points toward a more subtle relationship, where conscious observation participates in the natural processes through which potential realities become actualized. Your awareness might be woven into the fabric of realities becoming in ways that are both more intimate and more mysterious than classical physics suggested. The implications extend to contemplative practices and states of consciousness. Meditation traditions often emphasize the cultivation of refined attention and clear observation. If consciousness does play a role in quantum processes, then practices that develop greater sensitivity and clarity in conscious observation might involve learning to participate more skillfully in the fundamental processes through which reality is determined through conscious participation in information processing. The measurement problem in quantum mechanics ultimately points us toward questions that extend far beyond laboratory experiments into the nature of existence itself. Whether consciousness literally collapses wave functions, or whether these effects reflect deeper computational relationships between different types of information processing systems, the observer effect reveals that the boundary between mind and matter is far more mysterious than classical science assumed. As we continue this exploration, we encounter ideas that stretch beyond current scientific consensus into realms of speculation and possibility. Yet these speculative territories often prove to be where the most profound insights emerge, where the intersection of rigorous science and contemplative wisdom opens new ways of understanding our place in the cosmic order. In the depths of what we call empty space lies one of the most profound mysteries in physics. The quantum vacuum, far from being a void, seethes with activity at scales so small they escape direct observation. Virtual particles flash in and out of existence in time frames shorter than measurement can capture, yet their effects ripple through every aspect of physical reality. This hidden layer of existence might hold clues to understanding how reality emerges from computational processes. The Casimir effect demonstrates that this quantum vacuum activity produces measurable consequences. When two metal plates are placed extremely close together in a vacuum, they experience a slight attractive force that can only be explained by the behavior of virtual particles in the space between them. The confined space between the plates restricts which virtual particles can appear there, creating an imbalance in vacuum energy that pushes the plates together. This effect suggests that empty space itself has structure and energy content that responds to geometric constraints. In computational terms, the quantum vacuum might represent the background processing that maintains the basic operating system of reality. Just as computer programs run background processes that handle memory management and system maintenance, the universe might require continuous quantum computational activity to maintain the stability of space-time and physical laws. Zero-point energy, the irreducible minimum energy present in all quantum systems, provides another window into the computational nature of reality. Even at absolute zero temperature, quantum systems retain vibrational energy that cannot be extracted or eliminated. This residual energy might represent the computational overhead required to maintain quantum information processing in physical systems. The implications stretch toward understanding consciousness itself. If biological systems harness quantum effects for information processing, as some theories of quantum consciousness suggest, then living systems might tap into this background quantum computational activity. Consciousness could represent a specialized form of information processing that interfaces with the quantum vacuum's computational substrate. Take a moment to consider the space around you right now. What appears to be empty air is actually filled with quantum field fluctuations, virtual particle pairs, and zero-point energy oscillations. You exist within an ocean of quantum activity that might represent the universe's ongoing computation of reality itself. Your thoughts and awareness emerge from biological systems that interface with this quantum computational medium in ways we're only beginning to understand. The holographic principle gains additional significance when applied to quantum vacuum physics. If all the information in a volume of space can be encoded on its boundary, then the virtual particles and quantum fluctuations that fill space might represent computational processes occurring on distant holographic screens. What we experience as three-dimensional quantum vacuum activity might be projections of two-dimensional information processing occurring at cosmic boundaries. This perspective transforms our understanding of locality and non-locality in physics. Quantum entanglement, which creates instantaneous correlations between distant particles, might not require information to travel through space at all. Instead, entangled particles might access the same computational processes in the holographic substrate, creating the appearance of non-local correlation through shared access to underlying information processing. The hard problem of consciousness asks how subjective experience arises from objective physical processes. How does the firing of neurons create the felt sense of seeing red, hearing music, or experiencing joy? This question becomes even more intriguing when viewed through the lens of quantum information, processing, and computational theories of reality. Traditional neuroscience approaches consciousness as an emergent property of complex neural networks. Billions of neurons communicate through electrochemical signals, creating patterns of activity that somehow give rise to unified conscious experience. But this approach struggles to explain why there should be any subjective experience at all. Why shouldn't biological information processing occur without the inner dimension of felt experience? Quantum theories of consciousness propose that subjective experience might arise from quantum information processing in biological systems. Some interpretations suggest that consciousness represents the intrinsic first-person perspective of quantum computational processes. What we call qualia, the subjective qualities of experience, might be how quantum information processing feels from the inside. This doesn't mean that consciousness directly controls quantum events, or that meditation can influence particle behavior. Rather, it suggests that consciousness and quantum mechanics might share fundamental informational properties. If reality is computational at its foundation, then consciousness might represent a particular type of information processing that has natural relationships with quantum computational substrates. The binding problem in neuroscience asks how the brain integrates information from different regions and sensory modalities into unified conscious experiences. How does the distributed processing that recognizes a face, identifies a voice, and recalls associated memories combine into the seamless experience of recognizing a friend? Classical neural networks struggle to explain this unity of consciousness. Quantum entanglement offers a potential mechanism for binding distributed information into coherent conscious states. If different brain regions can become quantum mechanically correlated, these correlations might create the unity of conscious experience without requiring a central location where all information comes together. Consciousness might emerge from quantum informational relationships rather than from classical neural connections. As you reflect on these ideas, notice the quality of your own conscious experience right now. The seamless flow of thoughts, the integration of sensory experiences, the sense of being a unified self that persists through changing experiences, all represent remarkable achievements of information processing. Whether this processing involves quantum effects or purely classical neural computation, the emergence of consciousness from physical processes remains one of the deepest mysteries in science. Some interpretations suggest that consciousness might be more fundamental than previously assumed. Rather than emerging from complex arrangements of matter, consciousness might be an intrinsic aspect of information processing itself. In this view, even simple information processing systems might have minimal forms of experience, with complex consciousness emerging as information processing becomes more sophisticated and integrated. This perspective, known as panpsychism, suggests that consciousness might be a fundamental feature of reality, like mass or electric charge. Complex consciousness would emerge from the integration of simpler conscious elements, just as complex matter emerges from the combination of fundamental particles. If reality is computational, then consciousness might represent the subjective dimension of cosmic information processing. The universe appears to be remarkably well suited for the existence of stars, planets, and ultimately life itself. The fundamental constants of nature, from the strength of gravity to the nuclear forces that bind atoms, fall within extremely narrow ranges that allow for cosmic complexity. If these values were even slightly different, the universe would be either too chaotic for stable structures to form or too static for interesting phenomena to emerge. This fine-tuning problem has puzzled cosmologists for decades. Why should the universe have exactly the right properties to support the evolution of conscious observers like ourselves? The traditional multiverse explanation suggests that we exist in one of countless universes with different physical constants, naturally finding ourselves in one where life is possible. But the simulation hypothesis offers an alternative explanation that quantum physics makes increasingly plausible. If our reality is computationally generated, then the fine-tuning of physical constants might reflect intentional design choices made by the entities responsible for creating the simulation. The precise calibration required for a universe capable of supporting complex structures and conscious observers might be exactly what we would expect from a deliberately crafted virtual reality. This interpretation doesn't require supernatural intervention or violation of physical laws. Advanced civilizations with sufficient computational resources could design simulated universes with physical parameters optimized for complexity, beauty, and the emergence of conscious experience. The fine-tuning we observe might be evidence of sophisticated engineering rather than cosmic coincidence. The anthropic principle takes on new meaning in this context. Rather than being a tautological observation that we find ourselves in a universe capable of supporting our existence, it becomes a clue about the possible purposes and intentions behind reality's design. If consciousness represents a fundamental goal of cosmic evolution or simulation, then the universe's apparent optimization for the emergence of aware observers makes perfect sense. Take a breath and consider what this might mean for your existence right now. If the universe has been fine-tuned to support consciousness, then your capacity for awareness, wonder, and understanding might represent one of the cosmos's primary achievements. Your ability to contemplate these questions, to experience beauty, to form relationships, and to participate in the ongoing discovery of reality's nature might be precisely what the universe was designed to enable. This doesn't necessarily imply that every detail of existence is predetermined or that individual lives lack meaning within a simulated reality. Even in sophisticated simulations, emergent behaviors arise that weren't explicitly programmed. Complex systems develop their own dynamics, creativity, and unpredictability. If we exist within a cosmic simulation, the emergence of individual consciousness, free choice, and creative expression might represent genuine novelty within the system's computational framework. The fine-tuning of physical constants also extends to the mathematical elegance of natural laws. The equations that govern physical phenomena display a beauty and simplicity that many physicists find deeply compelling. Why should the fundamental relationships describing reality be expressible in such elegant mathematical forms? In a purely material universe arising from random processes, we might expect the laws of nature to be more arbitrary and complex. But if reality is computationally generated, mathematical elegance becomes a natural feature rather than a mysterious coincidence. Well-designed software typically exhibits mathematical beauty in its underlying algorithms. The elegance of physical laws might reflect the aesthetic sensibilities of cosmic programmers who valued mathematical beauty as well as functional effectiveness in their reality generation systems. The concept that reality might operate as a vast computational system gains concrete support from research into cellular, automata, and digital physics. These fields explore how complex behaviors and structures can emerge from simple computational rules operating on discrete information processing grids. The parallels between cellular automata dynamics and fundamental physics suggest that our universe might indeed function as a cosmic computer. A cellular automaton consists of a grid of cells, each existing in one of several possible states that evolve according to fixed rules based on the states of neighbouring cells. Despite their conceptual simplicity, cellular automata can generate patterns of extraordinary complexity and beauty. Some configurations exhibit behaviours that appear to move, reproduce, interact, and evolve in ways that mirror biological and physical processes. John Conway's Game of Life demonstrates how rich complexity can emerge from remarkably simple rules. In this cellular automaton, cells can be either alive or dead, with their future states determined by counting living neighbours according to basic rules for birth, survival, and death. Yet from these minimal specifications arise gliders that move across the grid, oscillators that pulse with regular rhythms, and even structures that can perform universal computation. The implications for understanding physical reality are profound. If simple computational rules can generate complex behaviours that mimic physical and biological phenomena, perhaps the laws of physics themselves are computational rules operating on a cosmic cellular automaton. Space might be discretized into fundamental units, with each region processing information according to quantum mechanical rules that determine its future states based on interactions with neighbouring regions. Edward Fredkin, one of the pioneers of digital physics, proposed that all physical processes could be understood as computations performed by the universe itself. In his view, particles don't move through space so much as information patterns propagate through a cosmic computational medium. What we experience as physical motion, force, and interaction might represent the execution of algorithms running on the universal computer that generates experienced reality. This digital physics perspective explains several puzzling features of quantum mechanics. the discrete nature of quantum energy levels, the probabilistic outcomes of measurements, and the apparent pixelation of reality at Planck scales all align naturally with computational models. If space and time are fundamentally discrete rather than continuous, then physics becomes a matter of information, processing, rather than smooth mathematical functions. The speed of light limit gains new significance in this framework. Rather than representing a fundamental property of space-time geometry, the cosmic speed limit might reflect the maximum information propagation rate in the universe's computational substrate. Just as computer processors have maximum clock speeds that limit how quickly they can execute instructions, the universal computer might have processing limitations that manifest as relativistic effects. Take a moment to imagine yourself existing within this cosmic computation. Every thought you're having, every sensation you're experiencing, every interaction between the atoms in your body might represent the execution of algorithms in the universe's vast information processing system. You wouldn't be separate from this computation, but rather a complex pattern within it, a conscious subroutine in the cosmic program. Quantum computers provide additional insight into how reality might function computationally. These devices harness quantum superposition and entanglement to perform calculations that would be impossible for classical computers. If the universe operates as a quantum computer, it could maintain superposition states for unmeasured systems, while computing definite outcomes only when conscious observation requires them, exactly as observed in quantum mechanics. The error correction mechanisms discovered in quantum computing research parallel features we observe in fundamental physics. Quantum computers require sophisticated error correction protocols to maintain coherent quantum states in noisy environments. Similarly, the universe displays remarkable stability in its physical constants and conservation laws, despite the chaotic complexity of real-world systems. Some interpretations suggest that apparent anomalies in physics might represent error correction processes in the cosmic computational system. When experimental results change unexpectedly, or physical constants appear to drift slightly, these could be instances of universal debugging, where the underlying information processing system corrects accumulated computational errors to maintain consistency. Physicist John Wheeler's revolutionary insight, it from bit, suggests that all physical phenomena arise from binary information processing at the most fundamental level. This idea transforms our understanding of matter, energy, and space-time from substantial entities into patterns of information processing. In Wheeler's vision, the universe isn't made of things processing information, but rather of information processing that creates the appearance of things. This information-theoretic view of reality gains support from multiple areas of physics. Black hole thermodynamics reveals that these cosmic objects have entropies proportional to their surface areas rather than their volumes, suggesting they encode information in fundamentally discrete ways. The holographic principle extends this insight, proposing that all the information in any volume of space can be represented on its boundary. Quantum information theory provides mathematical frameworks for understanding how information behaves in quantum systems. Quantum bits or qubits can exist in superposition states, holding more information than classical bits, while remaining subject to fundamental limitations on information extraction through measurement. The processing of quantum information through entanglement, interference, and measurement closely parallels the strange behaviours observed in quantum mechanical systems. If reality is fundamentally informational, then the particles, forces, and fields we study in physics become patterns of information processing rather than independent material entities. An electron wouldn't be a tiny sphere with definite properties, but rather a stable pattern of quantum information that maintains its coherence through ongoing computational processes. The apparent solidity and persistence of matter would emerge from the reliability of these information processing patterns. This perspective transforms our understanding of physical laws from descriptions of how matter behaves to specifications for how information processing should proceed. The conservation of energy becomes a constraint on information processing operations. The speed of light limit becomes a processing speed limitation. The uncertainty principle becomes a fundamental feature of quantum information processing rather than a limitation on measurement precision. Consider what this means for your existence right now. If reality is informational, then your body, your thoughts, your memories, and your capacity for experience all represent patterns of cosmic information processing. You wouldn't be made of matter that processes information, but rather of information processing that creates the experience of material embodiment. This doesn't make your experience less real or meaningful. Information patterns can be just as stable, complex, and beautiful as material structures. A symphony exists as information patterns in sound waves and neural responses, but its beauty and emotional impact remain profound. Similarly, if consciousness arises from information processing patterns, your awareness, relationships, and creative expressions retain their full significance. The emergence of complexity from simple information processing rules provides a model for understanding how rich realities can arise from computational foundations. Conway's Game of Life and similar cellular automata demonstrate how simple rules operating on discrete information can generate patterns of stunning complexity and apparent intelligence. The universe might operate according to similar principles, with the vast complexity of physical reality emerging from elegant information processing algorithms. As you reflect on these ideas, notice how they invite a shift in your relationship with physical reality. Instead of imagining yourself as a material being observing an external world, you might consider the possibility that both you and the world arise from the same underlying information processing substrate. The apparent separation between observer and observed might be a feature of how cosmic computation creates the experience of distinct perspectives within a unified informational reality. The intersection of quantum physics and simulation theory has moved beyond philosophical speculation into the realm of testable scientific hypotheses. Researchers around the world are designing experiments specifically intended to detect whether reality operates according to computational principles. These investigations represent some of the most profound experimental programs in the history of science, potentially capable of revealing the fundamental nature of existence itself. Former NASA physicist Thomas Campbell has proposed a series of experiments based on variations of the double slit and quantum eraser configurations that could provide evidence for what he calls virtual reality physics. These experiments are designed to test whether quantum systems behave differently when observation occurs versus when information is merely available to be observed, even if no conscious being actually accesses that information. The key insight behind these experiments is that a computationally generated reality might optimize processing resources by only computing definite outcomes when conscious observation actually occurs, rather than maintaining definite states for all systems at all times. This would be analogous to how video games only render detailed graphics for areas currently being observed by players, using computational shortcuts for regions that aren't being actively viewed. One proposed experiment involves creating quantum interference patterns that should disappear when detectors are placed to observe which path particles take through a double slit apparatus. The crucial test involves temporarily storing the witch path information without immediately observing it, then later choosing whether to actually look at the stored data. If reality is computationally generated for conscious observers, the interference pattern might only disappear when the information is actually accessed by consciousness, not merely when it's available to be accessed. These experiments remain technically challenging, and their results would require careful interpretation. Even if they produce results consistent with computational reality hypotheses, alternative explanations based on conventional quantum mechanics would need to be carefully considered. Science progresses through the accumulation of evidence rather than single definitive experiments, and these investigations represent important steps in a longer research program. The development of more sophisticated quantum computers provides another avenue for investigating the computational nature of reality. As quantum computers become more powerful, they offer unprecedented tools for simulating quantum systems and testing the limits of quantum information processing. Some researchers propose that sufficiently advanced quantum computers might reveal computational signatures in the behavior of simulated quantum systems that could inform our understanding of whether natural quantum systems are themselves computational. Take a moment to consider what it means to live during this remarkable period in human history. For the first time, we possess both the theoretical frameworks and experimental capabilities to seriously investigate whether reality itself might be computational. Whether these investigations ultimately support simulation hypotheses or reveal other surprising features of quantum mechanics, they represent humanity's deepest inquiry into the nature of existence. The search for computational signatures in quantum mechanics also extends to cosmological observations. Some theoretical models predict that if our universe is simulated, certain signatures might be detectable in the cosmic microwave background radiation or in the large-scale structure of galaxies. These signatures could include subtle periodicities or discretization effects that reflect the computational grid underlying reality simulation. Advanced statistical analysis of cosmological data might reveal patterns that suggest underlying computational processes. However, distinguishing genuine computational signatures from the natural mathematical relationships that characterize any well-ordered universe presents significant challenges. The elegance and mathematical beauty of physical laws could reflect either computational origins or fundamental mathematical principles governing reality. As these experimental and observational programs develop, they raise profound questions about the implications of their potential results. If evidence emerges supporting computational models of reality, how would this change our understanding of consciousness, free will, and moral responsibility? If we live within a simulation, what obligations might we have toward other potentially conscious entities within the same computational system? These questions extend beyond science into philosophy, ethics, and meaning. They invite us to consider not just what reality is, but what it means to exist consciously within whatever reality we inhabit. Whether our investigations ultimately reveal a computational universe or something else entirely, the very act of questioning the nature of reality with scientific rigor represents one of humanity's most profound achievements. As we approach the end of our exploration through the quantum foundations of reality, we find ourselves in a place that might feel both familiar and strange. We began with questions about whether quantum physics might provide evidence that reality operates like a simulation, and we've discovered that the answer is far richer and more nuanced than any simple yes or no could capture. The observer effect in quantum mechanics remains as mysterious today as it was when first discovered over a century ago. Particles that behave as waves until observed, then suddenly collapse into definite states upon measurement, continue to challenge our most basic assumptions about the nature of reality. Whether this reflects the computational optimization of a simulated universe, the fundamental role of consciousness in physical processes, or something else entirely, remains an open question. The mathematical elegance of quantum mechanics, with its precise predictions and beautiful symmetries, could indicate either the sophisticated programming of a cosmic simulation or the natural mathematical harmony underlying existence itself. The discrete nature of quantum energy levels and the apparent pixelation of reality at Planck scales align with computational models, but they might equally reflect fundamental features of a mathematically structured universe. What we can say with confidence is that quantum physics has revealed a reality far stranger and more mysterious than classical physics ever imagined. The solid, predictable universe of everyday experience emerges from quantum foundations that are probabilistic, interconnected, and deeply influenced by the act of observation itself. Whether these quantum phenomena point toward computational origins or toward even more profound mysteries, they invite us to hold our assumptions about reality more lightly. The implications of our exploration extend far beyond academic physics into questions of consciousness, meaning, and purpose. If consciousness plays a fundamental role in quantum processes, then awareness becomes more than passive observation of an independent reality. It becomes active participation in the ongoing creation of experienced reality, moment by moment, through the mysterious process we call conscious observation. This doesn't grant consciousness magical powers to control quantum events or manifest desired outcomes through intention alone. Rather, it suggests a more subtle and profound relationship where awareness participates in natural processes that determine which possibilities become actualized from the quantum field of potential. Your consciousness might be woven into the fabric of reality's becoming in ways that are both more intimate and more mysterious than classical science ever suggested. As you sit with these ideas, notice how they might change your relationship with uncertainty and mystery. And in a classical universe, not knowing something feels like a temporary limitation that better instruments or cleverer theories might eventually overcome. But quantum mechanics suggests that uncertainty might be fundamental to reality structure. Not a bug to be fixed, but a feature that enables novelty, creativity, and the ongoing evolution of complexity. If reality is computational, whether through natural quantum information processing or through simulation by advanced entities, then the mathematical beauty we find in physical laws reflects the aesthetic sensibilities that guided reality's creation. The fine-tuning that allows for stars, planets, and conscious observers might indicate intentional design choices rather than cosmic coincidence. Your capacity for wonder, for asking these questions, for experiencing beauty and meaning might represent precisely what reality was designed to enable. But even if we exist within the most sophisticated simulation imaginable, this doesn't diminish the reality of your experience or the importance of your choices, a character in a beautifully written story doesn't become less meaningful because the story exists in language rather than in stone. Your relationships, your capacity for growth and discovery, your potential for wisdom and compassion all remain as profound as ever. The search for truth continues, guided by both rigorous scientific investigation and contemplative inquiry into the nature of consciousness itself. Whether quantum physics ultimately reveals computational origins for reality or points toward even deeper mysteries, the journey of discovery enriches our understanding and deepens our appreciation for the remarkable fact that we exist at all in a universe capable of supporting conscious awareness. Perhaps the most important insight from our exploration is not any particular theory about reality's ultimate nature, but rather the reminder that existence itself remains fundamentally mysterious and wonderful. We are conscious beings capable of questioning the nature of consciousness, aware entities investigating the foundations of awareness, patterns of information processing that can contemplate the possibility that reality itself might be informational. In this ongoing mystery, science and contemplative wisdom find common ground. Both traditions recognize that reality exceeds our current understanding and invite us to approach existence with humility, curiosity, and wonder. Whether we ultimately discover that we live in base reality or within the most elegant simulation ever created, the capacity for conscious inquiry that enables these discoveries remains one of the universe's most remarkable achievements. As you continue your own exploration of these questions, whether through scientific study, contemplative practice, or simply mindful attention to the mystery of your own existence, remember that you are participating in one of consciousness's deepest inquiries into its own nature. The questions we've explored together tonight will continue evolving as our understanding deepens and new discoveries emerge. The quantum universe, with all its strangeness and beauty, remains open to investigation and wonder, and you, as a conscious participant in that universe, carry within your awareness the capacity to participate in its ongoing self-discovery, one moment of conscious observation at a time. Deep in the quantum realm, something peculiar happens to the very concept of measurement itself. We often think of measurement as a neutral act, like checking the temperature or weighing an object, but quantum mechanics reveals that measurement is far more active and mysterious than we ever imagined. The act of measuring doesn't just reveal properties that already existed, it appears to participate in creating the properties we discover. This isn't simply about clumsy instruments disturbing delicate systems. Even the most sophisticated, non-invasive measurement techniques still trigger the collapse of quantum superpositions. The universe seems to distinguish between measured and unmeasured systems in ways that suggest measurement itself might be a fundamental process rather than just a human activity imposed upon reality. Consider the quantum Zeno effect, where frequent measurements can actually freeze a quantum system's evolution. Named after the ancient Greek philosopher who proposed paradoxes about motion, this effect demonstrates that the timing and frequency of observation can dramatically alter how quantum systems behave over time. It's as if the universe responds to the rhythm of conscious attention, adjusting its computational processes accordingly. Some interpretations suggest this resembles how sophisticated simulations handle computational resources. A video game might run detailed physics calculations only for objects currently being observed by players, using simplified approximations for background elements. The quantum Zeno effect could reflect similar optimization strategies in a cosmic computational system, where frequent observation requires more intensive processing and naturally slows down system evolution. Take a moment to reflect on what measurement means in your own experience right now. When you direct attention to the sensations in your hands, to sounds in your environment, or to the flow of your breath, you're engaging in the same fundamental process that plays such a mysterious role in quantum mechanics. The act of conscious measurement, whether applied to quantum systems or everyday awareness, involves the transformation of potential into actuality through focused attention. The quantum measurement problem extends beyond laboratory physics into questions about the nature of information itself. In classical physics, information exists independently of whether anyone observes it. A book contains information whether or not anyone reads it. But quantum mechanics suggests that information might be more relational, coming into definite existence through the interaction between conscious observers and quantum systems. This relational view of information aligns with computational interpretations of reality. In information processing systems, data often exists in potential forms until specific computational operations are performed to extract definite values. The apparent observer dependence of quantum information might reflect similar computational principles operating at the foundation of physical reality. Quantum mechanics reveals that reality is built not from definite things, but from relationships between possibilities. Before measurement, particles don't have specific locations, momenta, or even definite existence as particles versus waves. They exist as probability distributions, mathematical structures that encode all possible outcomes without committing to any particular one. This architecture of possibility challenges our most basic intuitions about existence. We're accustomed to thinking in terms of either-or categories. Something either exists or it doesn't, is either here or there, is either happening or not happening. But quantum superposition reveals a reality based on both and relationships, where systems can exist in combinations of multiple states simultaneously. The mathematics of quantum mechanics describes these superposition states through complex numbers and probability amplitudes. These aren't just convenient calculational tools, but appear to represent the actual structure of reality at its most fundamental level. The universe seems to be computing with probabilities, maintaining vast arrays of potential outcomes until measurement selects specific results. Wave functions, the mathematical objects that describe quantum systems, evolve deterministically according to Schrödinger's equation. This creates an interesting paradox. The evolution of possibilities is completely predictable, but the outcomes of individual measurements are genuinely random. It's as if the universe runs a perfectly deterministic program for computing probabilities, then uses genuine randomness to select which possibilities become actualized. This combination of deterministic probability evolution and random outcome selection resembles the architecture of sophisticated random number generation in computer systems. High-quality random number generators often use deterministic algorithms to create complex probability distributions, then extract random samples from these distributions. The quantum universe might operate according to similar computational principles. As you contemplate these ideas, notice how they might apply to your own experience of possibility and choice. Before you make a decision, multiple options exist in a kind of mental superposition. You can imagine different outcomes, weigh various considerations, and experience the potential reality of different choices simultaneously. The moment of decision collapses this superposition of possibilities into a definite course of action. This doesn't mean your choices are quantum mechanical in a literal sense, but rather that consciousness might interface with quantum computational processes in ways that create analogous dynamics at higher levels of organization. The experience of deliberation, choice, and commitment might reflect your participation in cosmic computational processes that extend from quantum scales to conscious decision-making. Some interpretations propose that consciousness itself might exist in superposition states until the moment of definite experience. Just as quantum particles can exist in multiple states simultaneously, awareness might maintain multiple potential perspectives until specific moments of conscious experience collapse these possibilities into definite subjective states. This remains highly speculative, but it offers a framework for understanding how consciousness might participate in the same fundamental processes that govern quantum mechanics. Your awareness wouldn't be separate from the quantum computational substrate of reality, but rather a specialized form of information processing that emerges from and participates in cosmic possibility management. Despite decades of experimental verification and technological applications, quantum mechanics remains profoundly mysterious. We can predict its outcomes with extraordinary precision, build quantum computers that harness its effects, and use quantum principles in countless technologies. Yet the fundamental questions about what quantum mechanics means for the nature of reality remain as puzzling as ever. This persistence of mystery isn't a failure of scientific understanding, but rather a doorway into recognizing how much deeper reality might be than our current concepts can capture. Quantum mechanics has revealed that our classical intuitions about the nature of existence represent only a limited perspective on something far more subtle and complex. The various interpretations of quantum mechanics, from Copenhagen to many worlds to pilot wave theories, each capture certain aspects of quantum phenomena while struggling with others. No single interpretation has achieved consensus among physicists, suggesting that quantum mechanics might be pointing toward truths about reality that exceed our current conceptual frameworks. If reality is computational, whether through natural quantum information processing or through simulation by advanced entities, then our inability to fully comprehend quantum mechanics might reflect the limits of understanding available to conscious entities existing within computational systems. We might be like characters in a sophisticated simulation trying to understand the nature of the computing system that generates their reality. This doesn't mean that continued investigation is futile, but rather that each new discovery reveals additional layers of mystery and complexity. The quantum universe appears to be inexhaustibly rich, with each answer generating new questions that lead deeper into the foundations of existence. Take a breath and allow yourself to rest in this uncertainty. In a culture that often demands quick answers and simple explanations, quantum mechanics invites us to become comfortable with mystery. Not the mystery of ignorance, but the mystery of recognizing that reality exceeds our current capacity for complete understanding. This humble recognition might be exactly what's needed for continued progress in understanding consciousness and its relationship to physical reality. If consciousness plays a fundamental role in quantum processes, then approaching these phenomena with the humility and openness characteristic of contemplative inquiry might be essential for deeper scientific understanding. The intersection of quantum physics and consciousness studies represents one of the most promising frontiers for expanding human knowledge. Whether this leads to revolutionary new technologies, profound insights about the nature of awareness, or recognition of even deeper mysteries, the journey of discovery continues to unfold. At the deepest level we can currently probe, reality appears to be made not of matter or energy in the classical sense, but of information processing relationships. This insight emerges from multiple converging lines of research, from black hole physics to quantum computation to theories of consciousness itself. Information theory, originally developed for communications technology, has become one of the most powerful tools for understanding fundamental physics. The entropy of black holes, the uncertainty principle, the second law of thermodynamics, and even the arrow of time can all be understood in informational terms. This suggests that information processing might be more fundamental than the physical processes we traditionally consider primary. In quantum field theory, particles emerge as excitations in underlying fields that fill all of space, but these fields themselves can be understood as information processing systems with particles representing stable patterns of information flow rather than discrete material entities. What we experience as solid matter might be the experiential interface to quantum information processing, occurring at scales both incredibly tiny and unimaginably vast. Energy, the capacity to do work and create change, takes on new meaning in this informational context. Rather than being a substance that flows between objects, energy might represent the computational resources available for information processing operations. The conservation of energy becomes a constraint on information processing, ensuring that computational operations remain consistent across different reference frames and scales. The flow of time itself might reflect the directional flow of information processing in cosmic computational systems. The arrow of time, which distinguishes past from future despite the time-reversible nature of fundamental physical equations, could emerge from the natural tendency of information processing systems to explore increasingly complex computational states. Consider how this reframes your experience of existing in time right now. The sense of duration as thoughts arise and pass away, the feeling of moving from past moments toward future possibilities, the way memories seem to connect you to previous experiences, all might reflect your participation in cosmic information processing that creates the experiential dimension of temporal flow. This informational view of reality doesn't diminish the richness of experience or the importance of physical processes. Information patterns can be just as stable, beautiful, and meaningful as material structures. A musical composition exists as information patterns in sound waves and neural responses, but its emotional impact and aesthetic beauty remain profound, whether we think of it as material vibrations or informational relationships. If consciousness represents a specialized form of information processing, then awareness becomes a fundamental feature of reality rather than an accidental byproduct of complex material arrangements. Your capacity for conscious experience, your ability to process information and respond creatively to new situations might represent one of the universe's primary computational achievements. As we near the end of our exploration, we return to perhaps the most profound question of all. What is consciousness, and how might it relate to the quantum computational processes that appear to underlie physical reality? This question sits at the intersection of neuroscience, quantum physics, philosophy of mind, and contemplative inquiry. Consciousness exhibits several characteristics that seem to parallel quantum mechanical phenomena. The unity of conscious experience, despite arising from distributed processing in the brain, resembles the non-local correlations observed in quantum entanglement. The binding of different sensory modalities into coherent perceptual experiences might involve quantum informational relationships that transcend classical neural connections. The hard problem of consciousness asks why there should be any subjective experience accompanying information processing at all. Why shouldn't biological computers operate without the inner dimension of felt experience? Some interpretations suggest that consciousness might represent the intrinsic perspective of information processing systems, the way quantum computation feels from the inside. This doesn't mean that consciousness directly controls quantum events, or that meditation can influence particle behavior through intention alone. Rather, it suggests that consciousness and quantum mechanics might share fundamental informational properties. If reality is computational at its foundation, then consciousness might represent a particular type of information processing that has natural relationships with quantum computational substrates. The observer effect in quantum mechanics takes on new significance in this context. Rather than consciousness mysteriously interfering with physical systems, conscious observation might represent the interaction between different levels of quantum information processing. The collapse of quantum superpositions upon measurement might reflect the integration of quantum information into the particular type of information processing that generates conscious experience. As you reflect on your own conscious experience right now, notice how awareness seems to have both unity and multiplicity simultaneously. You can be aware of thoughts, sensations, emotions, and perceptions as distinct elements, while experiencing them within a unified field of consciousness. This paradoxical combination of unity and multiplicity resembles the quantum mechanical superposition of states that can be both definite and indefinite simultaneously. Some interpretations suggest that consciousness might exist in superposition states until moments of definite experience collapse these possibilities into specific subjective states. Just as quantum particles can exist in multiple states simultaneously until measurement selects a particular outcome, awareness might maintain multiple potential perspectives until specific moments of conscious experience actualize definite subjective states. This remains highly speculative and lacks scientific consensus, but it offers a framework for understanding how consciousness might participate in the same fundamental processes that govern quantum mechanics. Your awareness wouldn't be separate from the quantum computational substrate of reality, but rather a specialized form of information processing that emerges from and participates in cosmic possibility management. The development of contemplative practices throughout human history might represent the gradual discovery of how to work more skillfully with these quantum informational aspects of consciousness. Meditation traditions often emphasize the cultivation of refined attention, equanimity in the face of changing experience, and recognition of the interdependent nature of self and world. If consciousness does involve quantum information processing, then practices that develop greater sensitivity and clarity in conscious observation might involve learning to participate more skillfully in fundamental reality generation processes. This doesn't grant magical powers to control external events, but rather develops greater harmony between individual consciousness and the cosmic information processing network in which it participates. Take a quiet moment to appreciate the mystery of your own awareness. The fact that information processing in biological systems gives rise to the felt sense of being you, with your unique perspective, memories, and capacity for experience represents one of the most remarkable phenomena in the known universe. Whether consciousness literally involves quantum computation or emerges through other mechanisms, its existence remains a profound puzzle that continues to inspire both scientific investigation and contemplative inquiry. The implications of quantum consciousness theories extend to questions of free will, personal identity, and moral responsibility. If consciousness involves quantum information processing, then your choices might emerge from quantum superpositions of possibilities that collapse into definite decisions through processes that involve both deterministic computation and genuine quantum indeterminacy. This could provide a middle path between complete determinism and arbitrary randomness, suggesting that conscious choice involves creative participation in quantum information processing, rather than being either fully predetermined or completely random. Your decisions might represent genuine creative acts within the cosmic computational system, contributing novel information to the ongoing evolution of reality itself. Whether or not these speculative ideas about quantum consciousness prove accurate, they point toward the remarkable fact that consciousness and physical reality are far more intimately connected than classical science assumed. The observer effect in quantum mechanics demonstrates that consciousness plays some role in determining physical outcomes, even if we don't yet understand the mechanisms involved. As we continue exploring these questions through both scientific research and contemplative practice, we participate in consciousness investigating its own nature and relationship to the physical universe. This reflexive inquiry, where awareness studies awareness, represents one of the most profound adventures available to conscious beings. The quantum universe, with all its mystery and beauty, remains open to continued investigation and wonder. And you, as a conscious participant in that universe, carry within your awareness the capacity to participate in its ongoing self-discovery, one moment of conscious observation at a time. The questions we've explored together will continue evolving as new discoveries emerge and our understanding deepens. In the end, whether reality proves to be a sophisticated simulation, a natural quantum information processing system, or something else entirely, the search for truth through both rigorous scientific inquiry and contemplative wisdom remains one of humanity's most meaningful pursuits. The capacity for wonder, for questioning the nature of existence, for experiencing beauty and seeking understanding, these qualities of consciousness remain profound regardless of the ultimate substrate that makes them possible. The quantum dance of consciousness continues, inviting us to participate with curiosity, humility, and appreciation for the magnificent mystery of being aware in a universe that has somehow given rise to awareness itself. In laboratories around the world, a new generation of experiments is beginning to probe the deepest mysteries of quantum mechanics with unprecedented precision. These investigations aren't just about understanding particles and waves anymore. They're designed to test whether the strange behaviors we observe in quantum systems might reveal something profound about the computational nature of reality itself. The delayed choice quantum eraser experiments we discussed earlier represent just the beginning of this experimental frontier. Researchers are now developing even more sophisticated tests that could potentially distinguish between different interpretations of quantum mechanics. Some of these experiments are designed to test whether quantum systems behave differently when information is merely available to be observed versus when conscious beings actually access that information. Consider what this means for our understanding of measurement and observation. Traditional physics assumes that reality exists independently of whether anyone observes it. A tree falling in an empty forest makes a sound whether or not anyone hears it. But quantum mechanics suggests something far stranger. The very act of potential observation seems to influence quantum outcomes, even when no actual observation takes place. Recent experiments with quantum delayed choice setups have pushed this mystery even further. Scientists can now choose whether to observe which path a particle took through an experimental apparatus, even after the particle has already been detected. Remarkably, this retroactive choice about observation appears to influence the results, as if the present decision somehow reaches back to affect what happened in the past. This doesn't violate causality in the traditional sense, but it suggests that quantum systems exist in states of potential until complete observational contexts are established. The implications stretch far beyond laboratory physics into questions about the nature of time, information, and the role of consciousness in determining physical outcomes. As you contemplate these experimental horizons, take a moment to notice how scientific investigation itself represents a form of conscious inquiry into the nature of reality. Each measurement, each careful observation, each precisely designed experiment participates in the same mysterious process that quantum mechanics reveals at its foundation. The act of questioning reality through scientific method might be more intimately connected to reality's structure than we've ever imagined. Some interpretations suggest that the advancement of scientific knowledge represents the universe's way of understanding itself through conscious observers. If consciousness plays a fundamental role in quantum processes, then scientific investigation becomes a form of cosmic self-exploration, where reality studies its own nature through the development of conscious understanding. The development of quantum computers provides another avenue for exploring these deep questions. As quantum computational systems become more sophisticated, they offer unprecedented tools for investigating the relationship between information processing and physical reality. Some researchers propose that quantum computers might eventually reveal computational signatures in natural quantum systems that could inform our understanding of whether reality itself operates according to computational principles. But these investigations raise profound questions that extend beyond technical considerations into philosophy, ethics, and meaning. If experiments eventually provide evidence supporting computational interpretations of reality, how would this change our understanding of consciousness, free will, and moral responsibility? What would it mean to discover that we exist within a sophisticated information processing system, rather than a traditional material universe? The search for answers continues through both rigorous experimental investigation and careful theoretical analysis. Whether these efforts ultimately reveal computational origins for reality, point toward even deeper mysteries, or lead to entirely unexpected discoveries, they represent humanity's most profound inquiry into the nature of existence itself. Throughout history, contemplative traditions have developed sophisticated approaches to investigating the nature of consciousness and its relationship to reality. These traditions, spanning cultures and centuries, have often arrived at insights that seem remarkably aligned with some of the stranger implications of quantum mechanics. This convergence between ancient wisdom and modern physics opens fascinating possibilities for understanding consciousness and reality. Meditation practices, for instance, often emphasize the cultivation of refined attention and clear observation. Practitioners learn to observe the arising and passing of thoughts emotions, and sensations with increasing subtlety and precision. This training in conscious observation might involve developing greater sensitivity to the same fundamental processes that play such mysterious roles in quantum measurement. The Buddhist concept of dependent origination suggests that all phenomena arise in dependence upon multiple causes and conditions, lacking inherent independent existence. This perspective bears striking similarities to quantum mechanics' revelation that particles don't possess definite properties until measured, existing instead in relational states that depend upon observational contexts. As we come to the end of this gentle exploration through the quantum depths of reality, we find ourselves in a place of beautiful uncertainty. We began asking whether quantum physics might prove we live in a simulation and discovered something far more profound. Whether reality emerges from cosmic computation, natural quantum processes, or mysteries we haven't yet imagined, consciousness appears woven into the very fabric of existence in ways that classical science never suspected. The observer effect, the role of measurement, the strange dance between possibility and actuality all suggest that awareness isn't separate from the universe, but intimately participates in its unfolding. Take a quiet breath and appreciate the remarkable fact that you exist as a conscious being capable of questioning the nature of consciousness itself, participating in reality's ongoing exploration of its own deepest mysteries.